In the climbing stairs problem, you find yourself at the bottom of a staircase. Knowing that you can take either one or two steps at any given time, you're faced with the question: how many unique ways are there to reach the top? But before we dive into solving this, let's walk through an example. Starting from the bottom of the staircase, you can take either one step or two. First, you decide to go for 2 steps. Now, you're back to the same choice: 1 step or 2. This time, you decide on just 1 step. After a few more choices like this, you're almost at the top, just 1 step away. However, if you're on the second to last step and choose to take 2 steps, you'll overshoot the top of the staircase and miss the goal entirely. Anyway, back to the happy part, where we took 1 step and ended on top of the staircase. The sequence of steps we took represents one way of climbing the staircase, given the rule that we can take either 1 or 2 steps at any given time. But the question remains: how many unique ways are there to climb this staircase? In order to solve this problem, we can start by using some simple recursion, and then build on top of it. We'll create a method that takes as a parameter the total number of steps the staircase has, so we can handle staircases of any length, whether it has 5 steps or 50. This is the method we'll call when running our code. We then create a helper method that tracks our current position on the staircase. Since we start at the bottom, we'll call this method with the initial values of 0 for the current step and pass down n, the total number of steps on the staircase. In the helper method, we know that from our current position, we have 2 choices. We can either take 1 step or 2. We can represent this with 2 recursive calls to this method. Whenever you approach a recursive or dynamic programming problem, it's always a good idea to think about how the problem unfolds with all its choices, and then set the boundaries of the problem rather than going through every recursive call in order and end up with a path that initially might be difficult to understand. Let's try this and build some intuition about how our recursion tree might look like. Notice that at every step, the number of cubes doubles. But there is an issue: our recursive calls never stop. The function literally makes a mess and will call itself indefinitely, or at least until we run out of memory and hit the infamous stack overflow. But at this point, we know that we can generate all possible solutions, even if our execution just spiraled out of control. All we need is for our cubes to check if they reach the last step or if they overshoot the staircase entirely. And those checks are called the base cases. These are the conditions that tell our function when to stop, ensuring it doesn't run forever and only counts valid paths. So when we've reached the top of the staircase, that means when the current step is equal to the number of steps, we can increment a variable as we've found a valid solution and return the execution flow. If we overshoot the top of the staircase, then we can no longer build into a valid solution, so we can simply return from this. Now we have a valid recursive solution for our problem. Let's run this and see how it goes. The cubes that land on the last step increment our number of paths variable, while those that go beyond that no longer build into a solution. But that's some interesting behavior. When the recursive calls enter the base cases, they start returning control to whatever methods call them in the first place. And this seems to go all the way back to the initial call. We can adapt our solution based on this observation. Let's make several key changes. First, we'll remove the global variable, as we'll no longer need it to track the number of paths. Then, we'll change the helper function return type from void to int and have it return the result. After that, we'll adjust the base cases. The cubes that land on the last step return 1, since they build into a valid solution, and those that overshoot the staircase return 0. After that, we can return the sum of the recursive calls. This is called the recurrence relation, and recognizing it solves the most important part of any dynamic programming problem. Let's run this. This approach not only simplifies our code, but also aligns perfectly with the principles of recursion and dynamic programming. By eliminating the global variable and returning values directly, our function becomes pure and side effect free, making it easier to understand and debug. I mentioned earlier that whenever we encounter a recursive or dynamic programming problem, it's always a good idea to think about how the problem unfolds and then set the boundaries of the problem rather than going step by step through the recursive calls. And this works up to a certain point. However, in order to further build on top of our solution, we need to take a look at the path our recursive calls follow. When we run our code, the path is that of a depth-first search traversal. This technique explores one branch fully before backtracking to handle other possibilities, diving deep to the base cases before retracing steps. But rather than the path itself, there is one interesting thing we can notice in this traversal. We compute the result for the fifth step quite early. Later, we find ourselves recomputing it. And it's not just the fifth step, we end up repeating computations for other steps as well. This seems like quite a waste. What we'd like is a mechanism that would tell us if a step is already computed and return its value rather than computing it again. And this mechanism is called caching or memoization, and it helps us store the results of expensive function calls so we can use them along the way. And when we add memoization on top of our recursive solution, we get a true dynamic programming solution. So to make use of memoization, we need to add a few things in our code. We start by creating a hash map or a dictionary. The keys will be the steps and the values will be the number of ways to get to the top of the staircase from that specific step. Then, whenever we enter a recursive call, we check our hash map to see if it contains that step on the staircase. And if it does, we can return its value. Otherwise, we compute it and store it in the hash map. Let's run this again and see how memoization reduces the time complexity of our approach. We can see that quite early on in our traversal, we compute the sixth and seventh steps, with the help of which we compute the fifth step. After that, whenever we encounter a step we previously computed, we reuse that value rather than computing it again. One important thing is that any dynamic programming problem solved with recursion and memoization can be converted to an iterative solution. The iterative approach is also known as tabulation. Consider a staircase with only one step. How many ways are there to reach the top? Well, one. With two steps, there are two ways, either jump on each step or jump directly on the second step. Since we discovered the recurrence relation, we can use it to calculate further steps with ease. Notice how we can use an array to calculate the number of ways to reach the top for any step, as long as we start with the initial values and build from there. To implement this in our code, if the staircase has either one or two steps, we can simply return the corresponding number of ways to reach the top. Otherwise, we can initialize an array, store the steps we know, and use a loop to calculate further steps. In the end, we return the value of the step we are interested in. The good news is that we can further optimize our solution. We are currently using an array to store our computations. But if we take a closer look at our array, notice that at every step, we only use the previous two values to compute the current one. We don't touch any of the values that were computed before that. Knowing this, we can adapt our solution to use three variables to store this information. And these are a couple of ways to approach the climbing stairs problem. Let me know in the comments below what you think. If you enjoyed this video, don't forget to like and subscribe, and hope to see you in the next one.